So last class, we studied simple random sampling and Bernoulli sampling. And one interesting part is that if you first use Bernoulli sampling in the step one, and step two, if check if the realized sample size is equal to n. So n is given, right? N is given. So n is expected sample size. What target sample size? And if the realized sample size is equal to the expected sample size, target sample size, then we accept the sample. Otherwise, we reject it. Okay. So then the final, if you do this two-step procedure, then finally you will get a sample, right? A sample with a sample size n. And their sampling probability are all equal, probably, right? Because you use the Bernoulli sampling in the beginning. And then intuitively, it should be equal to simple random sampling, right? Because you use Bernoulli, even though you use, so the Bernoulli sampling, here IID, right? This is IID. But because you conditional on, so you have a condition. So condition is this. So you conditional on this particular event. This is not zero, and this is n. This is n. So you condition on this event, then what the independence is broke down, right? Because you have a condition, so they no longer independent. And actually, it turns out that this is exactly another way of implementing simple random sampling, because if you look at the, so basically, if you look at the joint density, joint distribution of indicators, conditional on this event, right? This is condition. Then how to compute this conditional distribution? Well, you have a joint divided by, so actually should have an indicator. Right? So if you have this indicator, so that's the numerator. Denominator, so what is the random distribution of this random variable? Summation of II. So summation of II, this guy follows a Bernoulli distribution. No, I mean the binomial distribution. Right? You have a basically pi. You have a capital N independent sum, right? And with each one has a probability of success equal to pi. So then this is a Bernoulli distribution. So this is the density, right? This is the density over the Bernoulli random variable. That's the denominator. And numerator is just the joint density of Bernoulli. And then see this guy is equal to pi times summation II plus 1 minus pi to the n minus the summation II. So basically, let me write it again. Summation II minus times 1 minus pi to the summation I1 minus pi I. Oops, no. Maybe what is this? And capital M minus I, right? So then this guy is equal to pi to the n and minus pi to the n minus n. So that actually you have a nice cancellation. So this guy cancels with this guy. So you get eventually you will get just this constant 1 over this combination, which is actually this is the density of I on the simple and the sampling, right? But this is a joint density of the indicator, sampling indicators on the simple and the sampling, right? So that basically shows the equivalence between the rejective paranoid sampling and the simple and the sampling, right? So that's kind of interesting. Now I'm going to move on to today's lecture. Okay. So week 3, part 1. So I'm now going to move on to completely randomized experiment. So now we are talking about experiment rather than sampling. So today's class. So Neyman developed a finite population sampling framework to understand the randomized experiment. The finite population quantity for the parameter is a function of observations in the finite population. So this is what we are interested in, right? We could be interested in estimating the. So this is the individual treatment effect, right? Individual treatment effect, and then basically this is the population mean of the individual treatment. That is a kind of finite population quantity. So this could be a parameter. So here's some notation. So I use the subscript n to emphasize that this is the mean in the finite population of size n, capital N. So this is a finite population variance. And then, so this is the using the y1, right? This is the using the y0. This is a finite population covariance, essentially. So covariance between y0 and y1. So this is actually capital N. So then, okay. And also we have another notation, which is the finite population variance of tau. So you can see this tau is a yi1 minus yi0. So then this guy is indeed yi1 minus yi0 minus y bar 1 minus y bar 0, right? Square. So then you can expand zero plus I don't have a space. Let me write it in the next page. This is simple algebra, but let's do one by one. So you can basically expand. Just the algebra, right? So then this is S1 square plus S0 square minus 2 S01. Okay. So that basically has this established the relationship in equation 1. So now, so far this is just the population quantity. So we don't have any randomization yet. So now we introduce some randomization. So the idea is we have a choice of treatment, right? Equal 1 or equal 0 under some random mechanism. So t equal 1, so this is essentially a treatment indicator. So t equal 1 is a treatment. So you observe y1. T equal 0 is a control. You observe y0. Right? T equal 1, we observe y1. T equal 0, we observe y0. So then t, the vector, the whole vector of t, plays the role of the you know, play the role of the sampling indicator in the sampling design, right? So it's essentially same structure. So we have we can name it as a treatment assignment mechanism. So then N1 is a summation over Ti, which is the sample size for the treatment group, and N0 is the sample size for the control group. Then the simplest possible design for experiment is a completely randomized experiment. Okay, so that is actually same as a simple random sampling in the sampling design, right? So it's the same structure. So basically, completely randomized experiment assignment mechanism is just the equal probability. Given, so this is fixed, right? This is kind of fixed. Given this number, then we basically consider all possible allocation or all possible sample with this assignment mechanism. I mean, with this sample size for the treatment group. And then put equal probability. So that is a sampling design. So you can see exactly the same structure with the as the simple sampling design, right? So it's essentially the same. But the estimator, the parameter is different, right? In the simple sampling, I mean in the sampling context, we are interested in population mean or population total, single finite population. While in experiment context, causal inference context, we are more interested in estimating tau, right? Which is the basically a function parameter defined on the counterfactual outcome. I mean the potential outcome. So it's more like a two population, in some sense. And then difference in means time, right? It can be written as this. And then sample estimator. So this is a estimator, right? Estimator in the sense that we can compute it from the sample. We can compute it from the sample. So this is, and then this is the estimator for the tau, which is kind of mean difference. And then we have an estimator for the finite population quantity. So then this is basically you have a treatment group sample, right? Treatment group sample and compute the S square. And this is the control group sample, and you compute the S square. Okay. First observation is that on the Sutba, so on the Sutba means that yi equal to ti yi1 plus 1 minus ti yi0. So, so then if I use that, right? So if I use that to here, yi ti times yi plus 1 minus ti yi0. If I use this definition to here, to this place, then what? Then this ti, right? Ti is either 1 or 0. So this ti multiplied to ti is just ti squared, which is ti. But ti times 1 minus ti is equal to 0. So the second part goes away, right? So the same way, if you apply to here, the same story, right? Ti times 1 minus ti is 0. And then you have this one only remain. So basically, you have another expression for tau hat using potential outcomes. So you do not directly observe potential outcome, both potential outcomes, but you observe one realization among the two, right? So if t equal to 1, you observe y1, t equals 0, you observe y0. So that means you can write it this way too. And now we conceptually we can consider finite realized finite population, right? So so this is a finite population with so they are fixed population quantity, and then the randomization is essentially a sampling over this f, right? So the treatment assignment is exactly equal to that of the simple sampling without replacement. So let's take a look what it means exactly. What so if you now the expectation is conditional on f. So conditional on f means we are the expectation we are referring to is only with respect to ti, nothing else, right? Because once f is given, right? This is a fixed. So f is give conditional. If you conditional on f, there's no randomness in y. And the only randomness is Ti. So then basically you have so you can see that this is a kind of a written in blue color to emphasize. So so basically this one is what Ti is a kind of simple undersampling. So we have something like this. So N0 given. So the expectation of Ti is capital N1 divided by N. So that basically is you have a N1 cancel. And then you get 1 over capital N outside. And then you have summation. Same way, N0 cancels each other. So you get this. So this is exactly equal to what? So this is tau n bar, right? Finite population quantity. So the randomness comes only from the treatment assignment. Yeah.
If without the condition for F and to define things like the next space, what about the range?
So I'm not so right. Randomness, we'll worry about that later. Here we only conditional on F. So when we say conditional on F means that we treat this one as a fixed, even though it's random, right? So F, so that's a good question. So why is that actually could be viewed as a random, but once you conditional on them, right? Once you put the conditional expectation, conditional on F, you are treating it as a fixed for now, right? And then we'll worry about the randomness of F later. Yeah, thank you.
But how can we justify how the calculation? I mean, it's like the range Utah.
Huh?
I know you know, it's like I'm just like thinking about like if we fix the if we like treat the TI as a random, right?
Yeah, it's random, yes.
And then how can we justify it? We know we have like the potential outcome, right? We only observe just one. But like, how can we justify it?
Well, we are not making an assumption. We know that. So the distribution of TI is under our control, right? So statistician, right? Actually create the randomness. So in that we are the God in that experiment. So in the observation study later, TI the true mechanism for TI is unknown. So we have to make some assumptions. But in the context of experiment, it's completely under our control. So we randomize and so we determine who's going to be in the treatment group and who's going to be control group by using design and so okay. So now, so the mean part is relatively easy because you take the conditional expectation with respect to TI, and then we know this property. So now we'd like to compute the variance. And the variance is also conditional variance, the condition on F. So then we want to compute the variance due to treatment assignment mechanism. And turns out that this is the formula. So this one looks complicated, but let's take a look at this one by one. So I'm gonna uh, so I will move on, show this proof, and then come back to its interpretation. So how to compute the conditional expectation? So remember, this is more very similar to computing the variance under simple non-sampling, right? Because this is essentially a kind of a sample mean, I mean, two sample means, and then they are selected by simple non-sampling. By the way, I said, the first homework was given, so you can the deadline is this Thursday. Some of the homework problems requires this kind of technique. I mean, computing the variance, and so maybe what I covered today's class could be relevant. So okay, so this is actually exactly same as a simple non-sampling, because we know TI. So what is a TI? TI is you have a population of size capital N, and then you select, right? You select a sample of size N1. So TI equal to 1. Oops. Right? So TI equal to 1 will be so this is the population sample. TI equal to 1. So this is essentially a treatment group sample, right? So treatment TI equal to 1 will be a treatment group sample. But we already know what is the variance covariance structure of this TI, right? It's because it's essentially simple as sampling. So simple and sampling design, we know. So the only difference is that in the simple and sampling, we code it, right? We have something like this. But now the sample size N is actually in our context, this is N1 is N. Capital N1 is N. Other than that, yeah, exactly the same. So the covariance between Ti and Tj is if Ti equal to 1, then it's just F times 1 minus F. By the way, F is originally sampling rate. So in our context, this is a simple random sampling context. But if it's a completely randomized experiment, this is N1 divided by N. Because N is equal to, sample size N refers to capital N. So this covariance, so I'm not going to repeat deriving this covariance because this is already covered in simple random sampling part. So I will assume that this is derived, but this is already we know that already. So now I'm going to use this property and move on to showing the variance, right? Okay, so let's take a look at the, so remember tau hat is a mu1 hat and mu0 hat. So the first part is a sample mean of y in a t equal 1 group. Y mu hat 0 is the sample mean in the t equal 0 group, right? So which is basically this one. And then you can so first equality is just we just subtract by so if you right and one inverse ti yi 1 minus y bar 1 will get minus 1 times y bar 1. So the algebra, because ti, summation of ti is capital N1, so it's just the ratio is just 1. So this is basically the second term is constant. With respect to the sampling, mechanism, right? The treatment of sampling mechanism is constant. So the variance is the same. So that basically shows the first equality. And then second equality, remember that, so when it comes to solving whatever mathematical problem, you need to first understand that which one is random, which one is not, right? So what is random here? The only thing random is this guy. This is random variable. Everything else is fixed, essentially constant. So basically, this is a linear function, right? So linear summation of the random variable. And your problem is computing the variance. That's easy, right? I mean, how to compute, for example, how to compute the CI, XI, right? Compute the variance. How to expand the variance of this linear sum of the CI times XI, where CI is constant and XI is random variable. This one is what? CI square, variance of XI, plus double summation I not equal to J, CI, CJ, covariance XI, XJ, right? So that's pretty much one-on-one type, formula, and then we apply it. So that's this part. It's no problem. And then if you look at the blue one, right? So TI, we know the TI, variance of TI from the formula. And what is the variance of TI, TJ when I is not equal to J? We have the formula. Okay. So that basically this part comes from this formula. Okay. So if you say this one. So what really we want to compute is this equivalence. So this is involves, this is not difficult because it's just algebra, right? You're supposed to simplify the summation, double summation, but this is maybe you probably want to understand the technique behind simplifying this algebra. So the usual technique is that you don't have to worry about this, right? This is constant. So this part is just constant. And then the only thing you need to worry about is considering. So basically you have a I not equal to J, CI1, CJ1. So how to simplify this, right? So that's basically let me. So, okay, this guy turns out to be basically XCI1 square minus Ci1 squares. Okay. So this is essentially cross product, right? Cross product over I not equal to J, which is actually square minus this. And then what we want to use is that this guy is equal to 0. The summation of Zi is 0 because of the definition of Zi. Zi is a mean subtracted random variable, right? Zi has a subtraction. The definition of Zi is here. So this is 0. So then you end of the day, you get this guy is equal to minus of these squares, summation of squares, which is the same as this one, right? Which is kind of same as this one. Because the first summation, you can see that this, if you move this up, this is actually summation of the Ci squares. So you actually have the same quantity, but maybe the coefficients are different. So you just do some. So then the algebra is really easy, right? Because you just have f times 1 minus f over this summation, and then you have this f, right? This constant times minus over this summation, the same summation. So it turns out that so that basically gives you this form. Because you have a what f times 1 minus f common, right? In common. So the only thing is you have a 1 minus n minus over 1 over n minus 1. So which is basically n1 minus 1 over n minus 1. That's what you a plus actually, plus. Because minus and minus is plus. Which is this one. And then simplify, right? So then this guy is n1 over n, n0 over n. So you have a n1 square, which makes the n1 in the denominator, and then you have n1, so n square. So another way of writing is that this guy is actually 1 over n1 minus 1 over n square. In the simple random sampling, on the simple random sampling, the variance formula is this. Or you have that is a simple random sampling. So simple random sampling, the sampling variance of the sample mean is this form, which is actually the same as this. Cannot be different, right? I mean, it's the same design, same estimator. How can they be different, right? Cannot be different. So, but anyway, just compute it again. So yeah, survey sampling and experiment. I mean the causal inference have some tedious algebra calculation. So you should be familiar with this technique. Which is good actually. You have if you have some hurdle, right? Then people may not be cannot get into the area easily. So if some topic is very good, but also easy to assess, then competition will be high, right? Then you don't have any special edge. So actually this kind of tedious algebra is actually is a hurdle, but at the same time it can be a protection. So it's a kind of a double-edged situation. Okay. Same way, right? Same way you can compute the variance of this guy. So we just look at the variance this guy, first one, and the variance of the second part is exactly the same with the 0 and 1 reversed. And now what we are interested in is actually the covariance now. So covariance is new, so I like to be careful on deriving. So covariance, see, this guy is mu hat 1. This guy, oops, is mu hat 0. And so you want to compute the covariance. Okay. So first thing is to write in terms of the CI. So we subtract by mean to simplify the algebra later. So that part is okay. We already have this same technique. And then this guy, now you can see that which is conditional on F, right? The only randomness is about Ti. So we just expand it. Then the covariance can be written as essentially the covariance of because they are constant. This is constant. It's just constant. And then the covariance of Ti and 1 minus Tj is equal to covariance of Ti and Tj minus. Because covariance, right? Covariance between Ti and 1 is 0. Covariance of random variable and constant is 0. So the only thing left will be is this guy, which has a minus in it. Now the question is how to compute this one. Well, okay, so that has some extra algebra, right? So how to compute it may it take some time. So covariance Ti, Tj. That we actually know. This one. Right? You want to use that formula. So you don't have to prove it again. 1 minus n minus 1 f1 1 minus f1 if I not equal to j, and then f1 1 minus f1 if I equal to j. Okay, so we will use this formula and simplify the basically this double summation, right? Double summation of I, j, covariance Ti, Tj, Ci1, Ci0. Gj, 0. So we are interested in simplifying this. What should we do? Well, probably we need to first decompose the double summation into two parts, right? When I is equal to j and when I is not equal to j, right? So when I is not equal to j, right? When I is not equal to j, then we know that it is n1 f1 1 minus f1 ci, right? And then when I is equal to j, then double summation becomes a single summation, first of all. Because when I is equal to j, then double summation becomes a single summation. And then this one, it becomes f1 1 minus f, and then zi 1 zj 1. Oops, zi 0. Because no j, right? J is I. So then it should be. And then what should we do? So perhaps we wanna utilize the fact that I equal to capital N ci 1 is 0, something like that. Or 0 j. So we want to probably utilize how? Well, so this one, to be rigorous, this is I equal to 1 to n, and j, and so you could, okay, okay, plus same. So what I did was just to express this one into two summation. Uh, I should so this is not really correct because I should change it to positive into negative minus. Then this is correct. Of course, is what? Oops. I 1 I. Basically, this smells up. So I not equal to j is I or right. So we exclude the case with I equal to j, basically, right? So enumerate all of them first of all, and then subtract when I is equal to j, which is basically make the single summation. Okay. Why we are doing this? Well, once you do that, then first term is 0. Right? So this double summation is 0 because of this. So you end up getting, so basically you have something like 1 over n minus 1 plus 1 and double summation f1 1 minus f1 ci1 ci0. I mean, this one is same thing, right? So the sum of the two terms is equal to this. And then that is, you can write it as a, so because this guy is a n over n minus one. So this one, you can write it as n f1, 1 minus f1, s01. Right? Because you have an n goes outside, and then capital N minus one can come goes into the definition of S1, S01. Okay. So basically what I just proved here, showed here, is basically the whole thing, this whole thing is equal to n times f1, 1 minus f1, s01. Right? So that I proved, I just I have just proved this equal. And then maybe it's a simplification, right? So because this guy is a n1, n0, n square. So n1, n1 cancel, n0, n0 cancels, and this n times n as a cancel. So you end up you can get so one interesting part is that this one is does not depend on the sample size. So this covariance does not, so independent over sample size n1 or n0, right? It only depends on population size, capital N. That's kind of interesting because other terms, so here, okay, so let's write it. So this guy is, another way of writing is n minus n s1 square plus n0 minus. So this guy is a variance of mu hat 1. This guy is a variance of mu hat 0. And this guy is a kind of covariance, minus covariance, 2 times covariance of mu hat 1 and mu hat 0. And so of course this variance depends on the sample size. This guy depends on the sample size, but this one do not. There's some smell for the construction. I think they changed it something. Okay. So you can see well, this is the population variance of y1, and this is population variance of y0 in some sense. But this one is a covariance. The covariance is tricky because you never really observe y1 and y0 together, right? So there's no way you can estimate what this covariance is. You cannot naively assume that they are independent. No. Why should, right? Why they are independent? No justification. So the variance is not identifiable in general. Means you cannot really estimate it from the sample without making any strong assumptions. Okay. So this is another just a reflection or interpretation of the CRE, completely randomized design, in terms of a sampling point of view. Okay, if you have a sampling perspective, how you want to interpret it, interpret the result here, right? Or the result here, this expectation and variance. So this is actually a the result, a design-based result, in the sense that you use the design property, the randomization property. So point is, the first observation is that the treatment group in the sample is essentially selected by simple random sampling, right? And also the control group t equals 0 is also selected by simple random sampling. So that means you can use the property, design-based property of simple random sampling to obtain some result. So the result is 3. So if you recall the what we covered in the class, in the previous class, sample mean is unbiased for the population mean. So that is the first part, right? So on the simple random sampling, the sample mean, simple sample mean is unbiased for the population mean. So that's first one. And second one is that the variance, right? The sampling variance of the sample mean can be written as something like that. So that is actually the formula is using the sampling notation. Right? So in the class we learned something like this. But now the context is this n, sample size n, is either capital N1 or capital N0. Depends on, right? Depends on you view treatment sample as a sample, then that sample size is N1. If you view control sample as your sample, then sample size is N0, right? That's the only difference. And also, the third part is the sample variance is unbiased for the final population variance, which is this one. Okay, so these 3 properties are already we covered in the class. So we can use it. Okay, so that is actually fundamental, key idea of Neumann's randomization approach to causal inference. So Neumann's theorem is that he was interested in this design-based, how to use design. So how to make an inference without making any model assumptions. And so he was very interested in developing design-based theory, and this is his kind of conclusion. So on the completely randomized experiment, tau hat is unbiased for tau bar. And so that's already proved, right? And variance is this one. That's already also proved. So these 2 parts we already covered. Third part is not covered yet. So the variance estimator. So if I use a kind of a typical variance estimator, right? S1 divided by sample size and S0 divided. That is actually you can use this t-test, right? If you think about doing t-test, you are interested in computing y bar 0 minus 1, and then you probably want to variance of y bar right? So that is more like this. But that's this is what you would use. One-on-one type, right? This is so basically we want to have a different interpretation of what is logic behind all these t-test. So basically, if you do use this potential outcome framework and use the design-based approach, then your variance estimator is conservative in the sense that its expectation is greater or equal to that of true variance under the design. So conservative variance estimator is maybe acceptable in the sense that you have a wider confidence interval, so you are more safe, right? So okay, so how to how to show this? Okay, so okay, so first of all, let's check this formula more carefully. So if you check this formula, you can write it this way. And then you use the notation as tau square. But this is as tau square. And so our variance estimator actually estimates the first two terms. So true variance actually, sorry, this is actually capital N. Okay. So the bias of the variance estimator, you have something. You have this amount of bias, but this bias is positive, non-negative. Okay. So that's why, so we can say that this is conservative. Okay. So then, this, you may be a little bit disappointed, right? I mean, it's not really unbiased, right? I mean, the variance is not really unbiased. So maybe it's not really good, even though it's conservative, but that's not necessarily means that it's acceptable. So then here's another. So this is one part of the story, half of the story. The other half of the story is this part. So now let's consider a two-phase type sampling structure. So now we want to introduce model. Okay, so now we want to introduce the model. So previously we just treat y1 and y0 as a fixed quantity, right? And treat only consider randomization with respect to TI, but maybe we are not really so. So the presumption is that we are interested in, if you are really interested in estimating the population mean, finite population mean, maybe this is the best we can do. But we may not be really interested in that particular population mean. Rather, we are more interested in tau. So tau is, so we are interested in this quantity rather than this quantity. So it depends on what you are interested in. The conclusion might change. But the bottom line is this is actually unbiased for this, right? So you can view tau bar n as an estimator if we could we could observe the potential outcomes, two potential outcomes, but which we can't. So the two-phase sampling framework is has a very interesting tool to compromise. I mean, to understand the whole story. So the idea is, okay, let's separate out two randomness. So one randomness is in generating Y, the other randomness is in the assignment. So then you can kind of conceptualize that you have a finite population generated from a certain random model, right? You have a realization of random variable. So that's the usual statistical model-based type framework in the first phase sample, first phase. And then the problem is that you don't observe Y0 and Y1 altogether, right? You don't observe them. So then you need an additional thing, which is phase 2, which is like a randomization. So you have a randomization in the phase 2, and then you want to consider the randomness in the whole, right? In the two phase, not conditional on F. So then the parameter of interest is this guy, the average treatment effect in the model, not in the finite population. So then this is the kind of graph that I showed you before, but now you can have a more clear understanding. So you have a Stochastic model that is a kind of concept that your random variable, potential outcome random variable, come from a certain finite from a model. And then a finite population is a realization, right? So this is essentially IID realization. So you have a IID realization of your model to get a finite population. And then from the finite population, so you could have a subscript. From the finite population, you generate T. Right? You generate T and assign randomness and then observe Y for that part, right? So then you observe Ti and Yi, which is kind of this. So you observe one of the two, essentially. And now, what is the implication? The one implication is that now you want to, when it comes to computing the mean and variance, computing the expectation and variance, you need to consider two phases, right? The two-phase structure. So this is a phase 1. This is a phase 2. Phase 1 is an IID, so randomness generating Y. So in phase 1, Y is a random variable. In phase 2, T is random variable. Okay. So this is more like this: 1, 2, 1, 1, 2, 1, 2. So subscript T, subscript 2 means that you only consider randomness in T, right? Because it's about two phase, second phase sampling. This is a first phase. So now if you do that, but the conditional expectation, conditional on F, we already covered, right? Remember, I already covered the design-based, randomization variance, expectation variance already. So we can just use it, right? So this guy, for example, so we already, I have already shown this. And now, what is the expectation of a tau bar? Well, tau bar is just a random variable, right? So this is basically the sample mean, population mean of this guy. And they are IID. So then the expectation of this guy should be equal to tau. That is this. And then same story, right? Here we have this one already. And here you have this one already. And all you have to do is to evaluate the expectation and variance with respect to the model, the Shipa population model. But this is relatively easy because this is a random variable, right? Now you have a random variable y. I mean, y bivariate random variable. Essentially, you have a bivariate random variable, and you know you have a model, right? So you can express the mean and variance, all this as a model parameter, right? So now let's take a look. So what is this? So let's do it in the next page. So variance of what's going on? Okay. Variance. Sorry. So we need to compute the variance of tau bar n, which is variance of but they are IID. So that is actually fairly easy. Depends on so we use this model, right? So we under this model, we will get this one. And also the second part is expectation of one over n and 0 and 1 as 1 square plus n 0 and 1 as 0 square plus 2 as 0. Okay. Then that is should be because IID sample, right? So let's do it this way. Let's simplify this one is 1 over n1 minus 1 over n sigma 1 square plus 1 over n 0 minus 1 over n sigma 0 square minus plus 2 sigma 0 1. Okay. So the total variance is this guy. So this is 1. This is 2. 1 plus 2. Okay. So hopefully there could be some simplification. So you get cancellation. And so you get end of the day, you get n1 sigma 1 square plus n0 sigma 0 square. Yes.
E2 begins 2 over for the variance zero.
Sigma 0 1?
Yeah, it's 2 over 2 over because we know.
Yeah, thank you. Yeah. Thank you. That's right. Yes. So then you have cancellation, right? So that actually proves the this result. Okay. Yeah, sorry, I kind of was so that basically yeah, so this is all for today. We'll to continue next week, this Thursday.